Today I was quite intrigued with the question of whether a neural network can actually model programming if-else statements. So I myself haven't tried this out, and I'll be just as impressed or surprised or disappointed with the results as you would be. And so yeah, without further ado, let's get to coding it. So let me just start here. Can a neural network model if-else statements? Okay, so what we'll do here is we will give the neural network some training examples of a particular if-else statement constructed in increasing difficulty and see what the neural network can do. Likely we'll be using, I think we'll just be using mean square error. Mean squared error as the loss function. Maybe the neural networks are multi-layered perceptrons, but can be made more complex later. Okay, so yeah, that's what we'll do first. Let's start by defining a function one that takes in like an input x. Okay, maybe if x is maybe greater than 30, then return, I don't know, return 0, else return 1. Something simple like that. Yeah, this is just a very simple base case. So maybe we do a okay. So this basically generates our data based on the given function. Okay, and maybe like not just the function. Maybe we also want a list of. So the inputs will be the function, which is our desired function. And then maybe we have also x, which is like the range of inputs to generate from. Okay, so yeah, something like that. We can do that. So let's do it. So like maybe in x, right? So the x will specify the range that we want to generate from. So like for x, or maybe like input in x, or maybe for each in x. Okay, so we have maybe like, actually this is a very simple function. We can just return a variable like that, return function x, function I for I in x. And that's all for the generate data. That's all we need to do. Okay, so yeah, something like this, and then we can define our neural network now. So this generate data can be used for many different class. Actually, I'm thinking whether or not we still need to define this. It's just going to be a one line, but all right, I guess we'll define it. So yeah, let's do it. So import TensorFlow stf, import char from TensorFlow import keras. Okay, something like that. Yeah. So what we will do is we'll define our model. So maybe we have a model. Okay, so maybe what we'll do is we'll do like a functional method. Just copy and paste the functional API. Some examples of that: keras.input, layers.dense. Yeah, let's copy and paste this over here. Okay, and we'll start with some input. X. Shape will be like 1. Yeah, we are just taking only one inputs as 1. Then we will like go through like some dense layers and then like this. Oops. We just maybe do like that. X equals to layers dense. In this case, we just need to do like that. Then we have model equals to model, inputs equals to inputs, outputs equals to outputs. Did I do it correctly? Do it correctly? Let's just check. Yeah, keras.model. Okay, yeah, so that should be more or less summarizing what this is actually a very simple function. It's just like return a certain number if the I think the perceptron should be able to do this, like because you can now threshold on a certain value, so it probably can do that. But let's just see whether it can do it. So this should be able to do it. Maybe we just do a model.summary. Okay, so yeah, this would be one of the models. So just a single layer input and a single node. Yeah, this is the most fundamental model. And then yeah, let's just do some model.compile. Okay, and then like we can do like loss is mean square error. Let's copy and paste this so that it's easy to like do it. Okay, so model.compile loss equals to mean square error. Optimizer will be just use Adam. Okay, it not normally works quite well. Matrix accuracy, that's fine. So yeah, this should be a basic model.compile that we will use. And then the model.fit. If we can just like do a validation split like that, that's good enough. We can already see the validation accuracy from this line. Okay, so what's lacking is we need X train and Y train. So what we'll do is like that. X train equals to, so we have to use this function here, generate X train equals to maybe like list, or we can just do like a number like I for I in range 1000, something like that, 1000 data sets. So I think that's good enough. Y train equals to, actually we can just do this, we can, yeah, we can save this generate data function. I think not required. Just do this and then we can fit like this. So now let's see the I in X train. Yeah, we don't need X train and X test because we have a validation split term here, which should already give us the validation split. So let's just try to do this. This function is not defined. Function 1. Okay, so what we need to do is we need to convert them into NumPy arrays, which then TensorFlow can then convert them into. So we can just do this. We can just do this here. Okay, let's see whether or not we can actually get the model to learn something. Okay, so it looks to me like if we do like a if x greater than 30, return 0, else return 1, kind of seems to not be able to predict it well. Let's just try to do like model 40. Let's just see the predictions for that. List index out of shape. Okay, let's see how our x looks like. Our x is a single array like that. That's correct. And what's our y? Our y is just like that, 1111 followed by zeros. So all's good. Okay, so maybe I need to do one more bracket. Model dot array maybe. Yeah, okay. So what we'll get is we'll get answer 7.65. So I guess if we take a look at like a neuron would probably use a sort of thresholding that that is based on the bias, and then like if I use a linear function, it cannot bias it well. If I use a Relu function like that, especially if the term is like 0 or 1. So maybe what I'll need to do is I need to use a sigmoid over here as my model, and let's try to train it and see whether we get some improvements. So I'll train and test accuracy. So after I shift it to a sigmoid output, which buffers it from 0 to 1, it seemed to work pretty well. It seemed to be able to, it's around 0 now. So if we go like somewhere at 11, 12, 13, 14. So it looks like a sigmoid function was quite necessary in order to generate that. So like 30 is this. How about 31? Let's it learn how to get. So 31 is supposed to be a 0, and anything below 30 is supposed to be a 1. So the model has essentially learned to predict everything as a 0. Okay, that's because um, it wasn't actually learning. It has learned to predict everything as a 0. That's because the terms below 30 over here are rare. So one way to do this is instead of giving it like 1,000 data set, I'm just going to give it 60. Okay, let's just try this. So as to pause it to learn a bit. So you can see that the accuracy here is like that. Okay, let's do this so that we can see the output, right? So we can see that the output is supposed to be like 0 for all these terms here, and then 1 for the next few terms here, which in this case the model is not learning it. The model is outputting it as all zeros. Okay, I mean the validation accuracy is 1, yes, but that's because maybe the validation split consists of the zeros. But okay, so perhaps it might be better if we kind of do a train test split using scikit-learn, because then we can bias that according to the y values instead of like doing a random train test split. So we can do this sklearn.model selection import train test split. So let's do that. Okay, from sklearn.model selection import train test split. So let's do this train test split method, which helps us to split according to the data set. So we can do this train test split, arrays, test size, train size, random state, stratify. So the main thing is this stratify, which we can then use the class labels to stratify it. Means we have a split that has an equal amount of test labels. So let's do that. Okay, so we can do like that. X train, X. Let's see the model output. X train, X test, Y train, Y test. Y train, Y test equals to train test split. This one, okay, and then we split our arrays. In this case, X comma Y. Okay, test size is 0.1, and then random state we can just put as like maybe 42, or can be anything. Stratify, we'll stratify on Y, which means that we actually stratify this by making sure that the output labels have an equal representation. So if let's say the default output for like let's say if else statement here is 0 and 1, we have a equal representation for Y. Yeah. So we can do this, and hopefully the network can generalize better. You see now it's quite bad, right? And it, also I just use one dense output. So this is like a perceptron. Maybe this would be better if I have a second hidden layer. So we'll try that. I mean, I actually don't know how this would turn out, but let's try this. Okay, let's try this. Okay, we have a stratify here like that, and yeah. Okay, let's get all this out. X train, X Y train, and then the validation set over here. Model.fit needs to be called separately. So let's use model.fit. We try to, oops, model.fit keras. We try to use validation data. If I remember correctly, there's this term called validation data in model. So okay, let me Google model.fit here. Let me search for model.fit in the keras documentation. Model.fit. Yeah, so even a simple if else is causing a lot of problems for this. So we have a list for model.fit. Actually, just need to find what's the model.fit arguments. Let's see whether we have it in the quick summary at the top. There we go. Fit model.fit. Over here we have validation data. So what does validation data do? It's a tuple x value, y value. So let's do that. Validation data equals to y train, y test. Sorry, x test, y test. Okay, let's try this out. Okay, so you can see that the accuracy is now like 50-50. I mean, let's take a look. Let's take a look at what's x train. X train is this, okay, and then we can just like maybe sum up the number of x train greater than 30, which is 26. Okay, how about x train greater smaller equals to, so it's around there. It's around there in terms of the representation of the data. So let's see x test. X test is about 3 and 3. So yeah, indeed it's stratified quite almost quite exactly based on this, and you can see that the validation accuracy is 0.5. So what does that mean? Okay, let's just see what's the prediction of this. We convert this to a numpy value, and then we put this as an integer. Oh no, I cannot do like that. Not numpy dot d type int. Can I do this? I dot flatten maybe, or dot rebel. Yeah, we can have something like this. Okay, then we can then map int to this, and then like display this as a list. Okay, so if we map integer to it, it will all be zeros, which isn't very flattering. It means that our neural network is just predicting zeros, which explains this accuracy here. Okay, maybe you might say that like maybe this is too small network, right? Let's try a larger one. We give it 100 nodes. We give it 100 nodes for the dense layer. Give it 100. Oh, but if we do it like that, 100 nodes, we kind of need only one output layer. So we have to do like a dense, and maybe the output still be a sigmoid, because so this one could be like x is x, and then we can put the activation as Relu. Oops, this is inputs. So with one parameter as the input, 100 nodes in the center, and the output is just so the is a multi-layer perceptron with 100 nodes in the middle. Okay, so yeah, maybe I just show you how it looks like. So this is, I'm doing something like this. I'm doing this thing here with one input node, 100 hidden layers, and one output layer here. Okay, so that's what I'm doing with this network. And let's see how it trains to the model. Yeah, oh, what's happening? Tracing is expensive. I have no idea what what this is, but it does look like it's training, right? Let's try again. So accuracy is about 0.5, which means that actually the network is still predicting all zeros. Okay, maybe it's because of this. I need to set this to linear maybe. And still the network is setting it as all zeros. Okay, so I mean maybe I will need to like use SGD instead. stochastic gradient descent, maybe the learning rate was a bit too high. Again, you see actually this, okay, it predicts now very negative values, which is not what we want. So I still think it having as a sigmoid output would be better. So you can see that everything is still zero. It doesn't really predict one after, like, I'm surprised. I mean, I thought this would be a very simple function to predict. Yeah, like after, if let's say it's greater than 30, it's supposed to predict zero. And okay, yes, this is quite surprising. I didn't expect it to fumble in this kind of simple example. So we basically just want it to do a thresholding, you see. So yeah, so I was thinking with the neural network bias term, it would be able to counter using this as a bias minus 30, and then after that, using maybe a Relu activation function, it can then give either zero or a high value. Then we can do a sigmoid. Maybe 100 is too much. Let's try one. Maybe accuracy is the wrong thing to use here. Maybe we shouldn't use accuracy because like there's no accuracy here. Like, I mean, I can predict as X or Y, but I mean, I'm not rounding them up. So maybe let's just use a loss without, like, if you see the loss here is 0.25, 10 epochs. Target tracing, define your TF function and the loop. Okay, so you can see that the loss is still at 0.25. Okay, I guess let's try others. I mean, it might be that the loss function. Okay, all right. So there's one thing that I was thinking of is maybe the inputs are a bit too heavy in terms of the size of these inputs. Maybe we need to like normalize the inputs. So like we could do something like this, like x uh, divided equals to max of x to normalize it. Cannot do this. Okay. Okay, so just like let's just like bypass this. Okay. All right. I guess maybe we can do a map function over here. It's okay. We can just do this. So I just basically normalize my x. So you can see my x train and my x test are now normalized between 0 to 1, and hopefully this makes the neural network learn better. Okay, it's still not that great. Okay, another thing I was thinking of is maybe this batch size is too much. We only have 60 examples, so maybe the batch size can be 1. Okay, okay, kind of not really learning. If you look at this, you can see that it's still predicting 0 for everything. 600 examples. I'm surprised. A simple if else statement like this should be piece of cake for a neural network, but it's still taking so long to learn. Oh, it's learning, it's learning. Okay, but this might be because the heavy skewed representation that we have here, because like only the first 30 inputs are one, okay, while the rest are greater than one. So that might be, you see over here the validation loss is, so it looks like the neural network is indeed learning something, but it might be just learning to predict all zeros, and we will know for sure if we look at this output here of the neural network. And let's take a look. Okay, indeed it's predicting all zeros, as you can see over here. If I, okay, no wonder neural networks don't handle tabular data that well. You see, it's predicting all zeros. It's just this. Hmm. Okay, it means that a simple multi-layer perceptron going through is not sufficient to do it. Let's try more complicated models. Okay, let's try 100. Okay, let's try 100. Maybe this would work. That size maybe here 32. Okay, so the loss is like about 0.05. Okay, so you can see that it's still not predicting those as ones. Okay, what if I make like everything predicted as ones, because now my x, oh sorry, my y should be all ones now. So the neural network just needs to predict ones. Okay, it's not predicting the ones. Okay, so this is something of concern. It means the network is not learning well. It's probably maybe the loss function is not great. Okay, let's think about it. So we want to fit in this x train, y train. My batch size is 32. It's supposed to predict as all ones. Okay, no biggie. Let's do batch size of 1 then. There we go. Okay, batch size of 1 is learning already. But it's learning for some. Okay, maybe if we train for more epochs. There we go. All the losses are low now. See, almost there, almost there. It's almost predicting everything as one. Less this 4 up here. Okay, let's try maybe 30 epochs. So just from a random initialization to print out all ones, it did take the network a while to learn it. It's still not learning perfectly. See, over here still has zeros. I wonder how long will it take before it realizes to output all ones. Okay, maybe if I don't do this map integer, I just want to see how what this looks like. Okay, so it might be the case of this mapping integer part. Okay, it may not be, so maybe I should do a round instead of integer. Okay, good. So now we have everything as 1. Round 0 maybe. Oops. Yeah, so round, maybe you still need to map an in after that. Okay, so yeah, all ones now, so that's good. Okay, maybe we penalize the network a bit too much. It might be this rounding function that was the error. Okay, so now let's try maybe 10 epochs, see whether it can learn the all one function. And yes, it can. How about just 1 epoch? Actually, is it already trained? That's, yeah, it's actually quite nice already actually. Okay, so using a sigmoid activation, it can learn the all one function. How about if we use a Relu activation? Can it learn the all one function? No, Relu doesn't. So Relu is not good for this 0 and 1 output. Okay, sigmoid is good because we know the output is constrained between the range of 0 to 1. Yeah, so it means that the activation function needs to match very well with the output domain for it to work. See over here, it works with 1. Okay, let's try 60 now. Okay, 60 means half half. Okay, half of them will be greater than 0, half will be less than 0. Okay, with an initial training of 1 epoch, this is what we get. Only the first is 1, but it looks like it might be able, let's give it 10 epochs. It might be able to get it. It's learning, it's learning, it's learning. Awesome. Okay, let's take a look now. Um, Still not that great. Okay, let me just Let's do this to see how it looks like. Okay, so we do have quite a lot of zeros here. Okay, but those parts that are not zeros up here, they are not exactly that close to 1. Okay, maybe I need to let it train a bit more. Maybe I need to let it train a bit more and give it 20 epochs instead. Let me just delete all this stuff here. Dun, 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 dun. Yeah, I'm still not able to learn like this half as. See, in the end, it only predicts this as a 1. But the loss is actually quite low. Oh, I know why. I actually divided it by max. Okay, let's not divide by max then. Let's try to train it without dividing. Okay, no. This didn't work out too well. Probability still need to divide by max, and then what we need to do here is I divided by 60. So I normalize the input here. Okay, I normalize the input, and then what happened is I predicted it to be. Oh, actually, it's quite a good split. It's quite a good split. Until here, they predicted it as ones. You can see that 1 and then 0. So if we count the sum of ones, we are supposed to get 30. Okay, so it's almost there. Okay, it's almost there because uh we should get 31 ones because 0 to 30. So actually it's like perfect match. Okay, so all right, so we can conclude solve. Simple if else statement. Verdict is solved, but with quite a lot of tuning. A lot of tuning. Definitely it can't really work out of the box. Let's try just using like maybe only one dense layer like that. Can it work? Like one hidden node. So it's not exactly that great. It didn't really work too well. I mean, if it's just one node, maybe the loss function, it's not doing too well here. Yeah, just one node like that. Keras dot optimizes dot std. Let's try something like that. Maybe the loss needs to be a little higher. No, maybe the loss needs to be a little lower then. There, it's actually going down. It's going down really slowly. Yeah, so actually it's an art to get the performance out of this multi-layer perceptron system because it may not be actually good for this kind of tasks. Okay, let's go back to Adam. Okay, so this didn't turn out quite well. The loss is still very high. Okay, in fact, actually, I'm thinking, right, if this kind of thing, maybe mean square error is not the one we want to do. We want to do like categorical cross entropy. Okay, let's try categorical cross entropy, or we can actually just do cross entropy because the outputs is either 0 or 1. So this will mean that my actually I can do binary cross entropy for this problem. In my experience, cross entropy works better than mean square error because the neural network kind of uses cross entropy method better than it does trying to minimize a square. Yes. So binary cross entropy will take in like the true prediction is like this 0 1 0 0, and then what it will do is it will minimize the KL divergence between the two probability distributions. Okay, from logics is true is when you don't do a softmax over here at the end, which is what we will do. From logics equals to true. So yeah, we can do a binary cross entropy, see what happens, and then we use a from logics equals to true in order to basically see uh, what happens. Okay, let's see categorical cross entropy. Yeah, I don't actually want to do like 0 1 0. I just want to do like one single number. Yeah, instead of like doing 0 1 0 0, I want to do it like maybe it's called sparse categorical entropy. Sparse, is there a sparse binary cross entropy? Sparse categorical cross entropy. Yeah, then we can just give it. Okay, let's use sparse categorical cross entropy then. Okay, let's use this. Let's use this. I think cross entropy will work way better than it did in the previous one. Okay, so we just use this Keras losses sparse cross entropy. Okay, and the output will then be like 0 1, which is what we already give it. Okay, and actually this part, if we use sparse categorical cross entropy, we don't really need to specify anything. Okay, is there from logics equals to false? Okay, so we kind of need to specify from logics is true. Okay, if not, it will, and because it's not probability distribution yet. So okay, so what we'll do is instead of having only one output here, okay, we will need to have output of two. Okay, because then okay, this will actually tell us uh so here it can be a Relu already because this is categorical cross entropy. So we have this activation is Relu uh goes to 2, which then tells us like is it 0 1. Okay, and we can train it. So it's all 0 now. Okay, maybe we need to do like a softmax. It seems to be not learning here. Okay, it might be that the optimizer is too much of an okay. My model outputs two values, but why is it only outputting like one here? There's something wrong here. So I mean, if I call my model on one element like zero like one, supposed to give me two values. So give me two values here. But if I were to do like this, oh, it actually combines the prediction. So yeah, this means this is a 1 1 1 1, and then okay, so it means the way we interpret our data, if we do it like that, needs to change a bit. This one needs to be, but you can see everything is output as one because like the one is still higher. and the 0. So yeah, it turned out for this case like this is not exactly that good. Maybe we don't need to use this method here. We can just do like that. Will it work? No, still didn't work very well. You can see that y choose like 1, 2. Okay, yeah, it means that actually I'm also not a fan of doing this method. So let's revert back to the previous one where we actually use like a sigmoid at the end, okay, to do this. Okay, and then what we will do is we will use mean square error again. Then we will go back this. Optimizer equals to Adam. Okay, let's try again. Okay, so that didn't work out. So with just 1 unit for the middle layer is not enough. We try 10 units. You can see that there's some decrease. There's some training done if we use 10 units. So yeah, it's pretty much you need a lot of units just to model one if else statement like this. It's pretty surprising actually, because I would have thought that if you have a multi-layer perceptron, actually you may just only need one neuron to do this. You just basically do a Relu activation function, okay, Relu function, and then basically if it's below a certain threshold is a 0. If not, activation function will give you a 1 beyond that certain value. Yeah, so I have a very radical idea. I think maybe if we just use the activation sigmoid, that might be good enough. You know, yeah. Okay, so it does look like it's trading. It's trading a bit. We might need to give it more. So with just one sigmoid, I actually expect it to learn. Because it's just basically predicting zeros or ones. So you can see that over here, this part is a 1, and yeah, it looks like it's learning 26. Okay, let's okay, maybe we need to like increase our, we need to tune this a bit. So Kara stop optimizers, stop Adam, learning rate is 0.1. Let's try 0.1. There we go. See, loss is very good. So actually we don't need 50 blocks. I think 10 is enough already. Okay, so this was is actually the first most simple test. I expected it to do quite well. Didn't expect to take so long to tune it. Okay, 31, which means that it's correct. It has predicted correctly. I mean, we can even try, like, we can try to give it maybe the number 30, 0, number 31, 0, number 32, it's still 0. Oh yeah, because 30, so actually 30 is misclassified. 29, 0. Oh, okay, 28. Oh, because I didn't divide by 60. Yeah, 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 that makes sense. Yeah, so actually near the boundary here, you can attack the neural network because like just based on very small minute numbers, people have shown like even for CNNs, you can tweak the value slightly, do some pixel perturbation, and it can get you an adversarial attack. And that's because I think the neural network itself is not exactly learning like a proper if else statement. It's just trying to get a boundary of the decision function, as you can see over here. Okay, so this is the simple neural network. Okay, and I think with one sigmoid, that makes sense. Okay, let's try something even harder. Let's use this, and then instead of returning like 1 and 2, we can return x and x times 2. Okay, actually, before I do this, I like to try if I remove this thing here, does it still work? No, it doesn't. So I still need to do like this thing here. So maybe if I have a batch normalization layer here, so we can have like this x equals to layers dot batch or layer normalization. Yeah, maybe with that, okay, Terra's layer. So if we don't do layer normalization, I think it may not be able to handle it because neural networks don't exactly handle the normalization very well. So layer normalization normalizes the activation, okay, with 0 and 1. Okay, okay, so I should have done this. So we have a layer normalization layer here now. Yeah, removing my normalization factor here that I did. Let's see whether it learns. No, no. Okay, maybe I cannot normalize like the input. Mm, it should be able to work though. Should be able to work. Maybe the learning rate here needs to change. Okay, this is a bit too high. The loss went up. It's a bit too low. Okay, this is a bit too low also. Maybe 0.5. The loss is not going up any. 0.0001. Okay, batch norm then. If layer norm didn't work. You can see that the loss here is actually decreasing. Okay, but it's not exactly learning it very well. Yeah, the loss is not there. Yeah, in fact, this batch normalization might have harmed the performance here because yeah, it did not actually do it. Okay, so notice that normalization access within each example. So mean activation close to 0, actual standard deviation close to 1. I think this actually works, right? Let's see what other normalizations we have. Unit normalization layer. Okay, let's try it. Unit normalization. Oh, this must be a new layer that hasn't been implemented yet. Yeah. Well, okay. I guess for today's test, let's just assume that you know we normalize the input ourselves. Yeah. I guess I could create a custom layer that does this, that takes in the highest value input that we receive, and then we just divide by the highest value input. But as of now, this kind of seem to, okay, this one should be 0.1. Yeah, with this set of parameters, oh, this is 29. Okay, I'm supposed to get um, 31 values of 1. Okay, so maybe, no, this didn't work out too well. So you can see that it's very sensitive to hyperparameter optimization. Like zero point 0.1 is quite crucial to solving it. Let's try again. It reached 31. So with this set of parameters, it solved it. So let's try a more difficult function, a function 2, whereby the first part of the function is it just returns x itself, and then the second part of the function returns x times 2. So let's see how it goes. Okay, so this function 2, and we can do a similar model, I think. Yeah, but instead of using sigmoid, because in this case this x and x times 2, we use linear instead. Okay, and I think maybe having just one input may not be enough, but let's just try with just one input first. Okay, and then we just do the same code, I guess. Model.summary, like that. We can copy and paste this code as well. Oh, actually the loss is decreasing. Okay, and then we can do this. Maybe we don't do the sum first, we just do this first. Oh, 111111000. Okay, this because this is function 1. I haven't changed to function 2. No wonder it's still quite good. Okay, so with this over here, the stratify has to be removed. Okay, because we cannot afford to have like x or x times 2 being like there's no class here to stratify on. So let's just do this. So it's supposed to give me like 1 2 3 4 5 when it reaches like, okay, maybe I will do for the range 30 first as one of them, and then I'll do here as another one from range 30 to 60. So this part here is supposed to be x times 2, okay, and this part here is supposed to be x. So you can see that the neural network has hit like a fine middle ground here by just like increasing slowly, okay, which is okay. I mean, but it's because this is like more or less a linear regression. Like I already gave it one that's node. Let's try giving it a hidden layer using Relu like that. We try to see whether it manages to solve this function. The loss is indeed going down. Let's see. Here is still not that good yet. Here is around the same. Did I change the model? Oh, I didn't change the model. Okay. Oh, I know why. Because this is supposed to be X. Okay, so this is now how it should look like. See, loss is going down more. Okay, it's going down but coming up, which hints that the learning rate is a bit too much. There we go. So it does look like it's fitting better. Okay, so maybe a better way to visualize this will be to plot the actual versus predicted. So over here, I'm just gonna import from matplotlib.pyplot import plt. Okay, so this is a very standard import. Right? Oh, sorry, should be import this as plt. Okay, so what I want to do is I want to plot in this data. Okay, so maybe I just define a helper function here, like here, plot line 1, line 2. Okay, plt dot plot. Okay, line 1, Okay, color equals to blue, label equals to predicted, and then plt.plot line 2 color equals to green. Okay, label equals to actual, and then maybe we just do plot.legend and then plot.show. Okay, define my plot. Okay, let's do something like that. So then we can actually show this. Okay, we can actually plot this out, my plot. Okay, we can do the actual value for this. So we can do like y y0 to 30. So this should be coming first. Y0 to 30 like that. So you can see the predicted and actual like that. We can also plot over here. So you can see that the predicted is this jagged blue line, the actual is this. So over here, the actual itself, okay, maybe I should make this greater equals to 30 so that the plot will look nicer. It's just supposed to be two different lines here. Like one going from 30 to 60. Okay, let's see what my y is. 10246 until 58. Also the times 2 is at the beginning. So it's like this. And then the second part it's here is 0 to 60 and the second part is like that 0 to 30. So there's actually two parts to this function and both parts uh, I didn't really show that well. I mean maybe I could just do the entire function itself to make it look like nicer and just one plot it shows everything. Yeah, so it's like that, then comes down and goes up again. So this function is actually quite complicated. Yeah. In fact, we can also do a similar one for this thing above. So like we can visualize the function. Okay, let's run the run few codes again. This one, let me just copy and paste it at the top. Okay. I don't need this anymore. We can just straight away go to the visualization and you can see that it's around the same. Yeah. Let's try this again. I mean, sometimes it works perfectly, sometimes it doesn't. Okay, so yeah, it's like there's one part here. Maybe if I give it more epochs, it can. Ooh, oh, it still didn't reach the right prediction. Interesting. 20. Let's try the whole model input functions again. You can see that the loss is going down, which is a good sign for network training. Yeah, but it looks like there's one thing that is a little off. It's not predicting fully. It's not predicting fully. Hmm. I thought it was working well. Turns out that it wasn't. Okay, let's let's try this. Maybe in the there we go. Maybe it's because of the stratify here. It did not stratify the boundary cases here, which is fine. Yeah. Okay, if this function 2, the loss is decreasing too. Okay, but you can see that the predictor is like still not exactly going this trend. It's not showing this trend that we want to. Okay, I'm just thinking whether or not like it could be a result of this. Okay, we take away the normalization and see what happens. Okay, now we have a prediction like that, which makes sense. I mean, they are trying to minimize the mean square error. You don't want to over predict, right? Okay, now what I'm thinking of doing is I'm going to set this to be 300 and changing this to 600, and I see what happens. Basically, we give it more training data and see whether through mean square error is able to cut down on its loss drastically. Okay, so the actual is, oh, did it fit perfectly? I'm not too sure, but I don't see the actual anywhere. Oh, oh, because this should be 600 now. Okay, so it looks like it's still giving one line prediction, which I thought it might be easy for neural network to give like double line predictions like that and like that. Yeah, you see, it just gives like that. Why can't it give one line up here and one line here? I mean, it's also be piecewise linear, isn't it? Neural networks. Okay, give it 100 layers. Okay, so it just shows that I omniscient. I think we can have human level AI at some domains already, like for those domains that involve a lot of like look ahead search. In reinforcement learning, we do have like programs that are able to learn from self play, like AlphaGo, that can do it better than humans. But that's only in certain domains, like in grid light games. In vision, we can recognize things probably quite well. Yeah, but all these are very susceptible to adversarial attacks. Yeah, see, just modeling a simple if else statement, which is pretty understandable for humans, took so long. I mean, this is just a very simple if else. I was actually thinking of doing fizz bus in this stream, but it looks like it needs to be on the next stream instead because this neural network it just can't do this if else very well. I have to even normalize the data for it in order for it to work. Yeah, which is kind of cheating. I mean, it's like knowing in advance like what your input, uh, what numbers your inputs can be, and I'm telling the program, hey, I'm going to normalize it for you so you have an easier time. So if it, yeah, yeah. Of course, I do think that maybe in the next 10, 20 years, AI should be able to automate most processes, like factory processes and stuff. So like humans can probably do a lot of things. Self-driving cars should happen soon in the next 10 years. In fact, it's already happening now. It's just this one. This one is not a linear equation. This is a piecewise linear. I mean, if I were to draw it out, let me try to use the draw function here. It'll look like this. Can you see my drawing, by the way? I'm trying out this draw function. I'm not too sure whether it's visible. So it's something like this, where like it's greater than 30, so it means that this part is a circle. It's not a linear equation. It is okay. It's lagging. Yeah, this is not a great tool to use. Yeah, I prefer Zoom actually. Yeah, my Twitch studio, the drawing kind of lags. But basically, if you look at it, it is not a linear function, but it's a piecewise linear function. If you are talking about piecewise, like you can split the graph into two. Yeah, so if else statements are meant to be like that. They are meant to be a conditional loop whereby I think you know this, right? I mean, yeah, it's basically supposed to be a way to do different logics, logic statements to like the input. Yeah, but you know, neural network is more or less a feed-forward network that models one function. If you want it to model a piecewise linear function like this, you need to imbue it with quite a lot of like some domain knowledge. Like over here, I imbue it with the knowledge that the output is 0, 1. I gave a sigmoid which has an output range of 0 to 1. Then it works. If I use like a Relu or linear activation, it kind of didn't work. Yeah, now this is a little tougher. This is also piecewise linear, but it's not just zeros or ones. This is x and x times 2. So how is it? It still sucks. I mean, you look at this. Yeah, still requires some work to do. So if you want to do like an if else statement like this, okay, a simple approach like this may not work. I already gave it 600 examples. Maybe I changed the learning rate a bit. Oh, I didn't tune it. Oh, that's my bad. That was my bad. Okay, let's try tuning it. Okay, let's basically give it the knowledge that the output is the input is only between 0 to 600 and see how it learns. Oh, it's actually this normalization is super important. If you don't normalize this, right, your function doesn't work. Oh, you see the loss here is it's going up. It's going up. Oh, it's going down. Okay, yeah. How about you, Omniscient? What's your predictions for AI surpassing humans in all domains? Like what year will it be? If you are with Kurzweil, the person who wrote The Singularity is Near, then 2029 is when the AI will start passing the Turing test. 2035 or 2040, I think his prediction for the singularity is 2040. Yeah. So, yeah, that's it. It's kind of horrible, isn't it? Yeah. SGD maybe. Stochastic gradient descent. Doesn't look like it's going down. Okay, now the loss looks like it's going up. It's weird. Yeah, it's weird. We already gave it 100 here. We normalize the input somehow. Actually, it's like that. Predictor is like that. Mm, I mean, if I were to use an SVM for this, this might be much easier than using a neural network. A neural network just doesn't seem to be well tuned for this sort of thing. Yeah. If I do like x and x times 2, then it's not that great. X times 2. Hmm. Okay, let's try giving it more layers. If one layer doesn't work, maybe two layers work. Who knows? The loss function just doesn't look like it's dropping anywhere near what we want. Manipulate matter. Uh, okay, it depends on what AI we are talking about. If like those AI to synthesize biological proteins, then yeah, I would say that we have made progress. We can synthesize proteins in a basically we can imagine the protein structure quite well now, like with AlphaFold and stuff. Yeah, but manipulating basic chemistry, maybe that's not an AI thing. That's a physical law thing. But the AI probably can discover the physical laws and in so doing, yeah, manipulate matter, I guess, if you are talking about that. Yeah, but I don't think the AI can change physical laws, but you will find an optimal way to operate within those physical laws. Yeah. What a lousy prediction. You look at this, it just predicts one straight line. uh, okay, it's a bit too much. Let's try Adam. Okay, the loss is now not a number. Okay, I believe that should be working because like, okay, maybe if I change this to sigmoid, I don't know whether it will help better. It does look like it's learning. Okay, although sigmoid calculation tends to be a little slower. Yeah, so actually, if I give it sigmoid enough, because it's like x times 2, right? So sigmoid activation is, it might be better than Relu for this. Okay, we shall see. We shall see. The loss looks like it's decreasing, yet it's still a very high loss. Okay, let's see. Um, did I do something wrongly here? Did I do something wrongly here? Let's see. My X array is this, which looks okay. The X array is 0 to 1. This gives it this. See how this looks like. Yeah, so it's all 289, which makes this correct. Yeah, maybe the mean square error makes it like go towards the center. Perhaps I would use like mean absolute error. See, it's fitting better. Mean square error wasn't that great after all. And it has the sigmoid look because we imbue it with a sigmoid function. Let's use back the Relu thing. Maybe mean square error is not that great for high values because it leads to very large losses. So let's try this. Mean absolute error. So I'm using mean absolute error loss. Now it should be 0 if it's good enough. Does it look like it's lowering? Yeah, it's pretty interesting actually. Yeah. Okay, maybe I use Keras dot optimizers dot Adam. Maybe we use a higher learning rate. Yeah, looks better with the higher learning rate. We might even need to use a learning rate scheduler just to learn this, where we slowly decay the learning rate as we train the epochs. Definitely looks like it's learning something, right? See? Oh, almost there, almost there. We're almost there with it. 100. Nice. Okay, let's try to train this for, give it 30 bucks. Okay, so it means that mean square error may not be that great after all. Like it kind of makes the network tend to draw one line through the loss function propagation. So mean absolute error might be a better bet for large numbers. Or either that, or we could do some form of scaling to the output data. So instead of doing an output data that is unbounded, we can bound it between 0 to 1, like how we did for the inputs. that could work as well. But mean absolute error seems to be pretty robust to this. In, see, the loss is actually okay. Let's use the learning rate scheduler. Okay, so that we like decrease the learning rate. Okay, so maybe we okay not learning rate scheduler but decrease LR on plateau, reduce RLR on plateau callback. Okay, let's use this. Okay, monitor something, factor is what, patience is what. Okay, so that we can like decrease our learning rate accordingly, like that. So we have a reduced RLR here. We call this here. Okay, from ntf.keras.callbacks, import this. Okay, so we import this, we monitor our loss. Okay, we have a patience of maybe 2 epochs, and then we decrease it by a factor of 0.5. Okay, and our mean learning rate is 0.01. Okay, let's try this so that like when we have a case where this increased by 1, we can reduce our learning rate further. Okay, patience of 1 maybe. Okay, it's got TensorFlow. Reduce LR. Oh, I forgot to do this. Callback. Okay, maybe this callbacks is not in this, it's here. Yeah. Okay, so now we do a reduced learning rate scheduler. It's not really a scheduler, but if it's like once the loss has reached a certain plateau, we decrease the learning rate even more. Like if let's say something like that. So we try to get to the lowest possible loss ever. So we keep decreasing our learning rate. It's actually working quite well. Yeah. So there's a lot of ways to do learning rate. Some people do a learning rate warm up, then after that decay. So this learning rate paradigm actually impacts a lot of model performance, and people have been studying this quite often. I myself just prefer to use a learning rate decay on the loss function, not going because this I think rather than using predefined heuristics, it really based on the training and oh look, perfect, perfect, perfect. So I treat it as soft, okay, because I like to move on to the next one. So a bit more complex if else statement, soft with a lot of tuning. I treat this as soft, right? I mean, don't you think this looks soft to you? It looks soft to me. I mean, okay, let's try a little bit of out of distribution data. So within distribution data, maybe we try out of distribution data. So we can try this. Mm, maybe in range from 600 to 1200, and then the y can just be like function 2i for I in range 600. Not too bad, not too bad. Doesn't doesn't increase as linearly as expected, but still not too bad. This one is for the right side, and then this one is for the left side. So out of distribution data for the left side, maybe we do from negative 600 to 0. Here the same thing as well, negative 600 to 0. So the left side here, uh, it tends to go to 0 because I think it's the Relu function. Yeah, but I don't blame it. I don't blame it because we didn't give it days data. It's not realistic to expect the model to extrapolate that straight line, right? So I count this as a win for the neural network. So soft for the neural network. Okay, let's try the hardest example. probably continue this another day, but it's quite interesting. Let's try another function. Function tree. Okay, so now what I want to do is I want to do um, uh, okay, let's try modulo. Okay, yeah. Instead of doing this, we do a modulo. Let's not do repeated. Okay, we just do modulo. Okay, and then we can use the same network. Maybe another day I'll try to use like a triple if else statement and see what works. Okay, we have this input. Okay, copy and paste this. Da, 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 da. Then we use the same thing again, and then we see whether we can actually use this function tree. See whether it works. Okay, I'm quite interested to see it. Let's try out this one. And let's see whether a neural network can classify modulo, the function of modulo, return x, and return x times 2. We see that it can classify this well. And let us see. Yeah, it looks like it's not exactly, the loss is quite high actually. I think this architecture may not be able to do modulo after all. Because previously we've been doing piecewise linear, you see, one linear function like that and one linear function like that. But now modulo, it requires the input to jump here and there because of the modulo function. I'm not too sure whether a neural network can model that. Okay, because I know neural network don't model modulo very well. Okay, but if we do it as part of an if else condition, can a neural network do it? Can the neural network model modulo function? And we shall see. The actuals. Okay, we have to probably plot it like differently. So we have to do it by points. So let's go back to the start here. Okay, maybe we do an additional one. Okay, we should have a format. Like, okay, maybe we just need this. Yeah, by default, I give it a dash, which means that let's use an X as a format instead, so you can plot points, or you can use a dot. So you can see that the predicted is just one line, it follows the bottom line, but the actual output is actually going up and down. Okay, so it means that if there's sufficiently complex piecewise linear functions, a neural network is not able to model this that well. Okay, how do we do it then? How do we model this well? Okay, let's try to tweak this a little. Maybe give it 1,000 nodes. Okay, you see the validation loss not decreasing. It means that it doesn't really learn how to do the jump that well. This might need quite a bit of tweaking. Okay, I think this modulo might require quite a bit of work for the neural network to learn this well. I don't know. I don't know how to make this work. Yeah, this probably requires a bit of work. Yeah, I'm not even getting to the hard statements. I'm just doing a very simple if statement like this, and the MLP method just doesn't seem to work that well. I even scaled it, and it still didn't work that well. Or rather, I scaled the input. Yeah, I didn't scale the outputs. You can see that the loss is not exactly going down. Okay, with 1,000, it's taking a little while to train. I don't blame it. This is a bit harder. Yeah, so this is it's still sort of two piecewise linear functions, but it's piecewise linear in a jumpy order because of the modulo function. If it's even, it's the top. If it's odd, it's the bottom. Yeah, I think if I modeled it as like three separate chunks of linear functions, it will work pretty well. But doing this modulo jumping here like this, traditional MLP may not be able to handle this that well because it has no notion of what's even and what's odd. Okay, neural networks are not that capable at modeling the modulo function, and that has to be inbuilt somewhat into the network for it to learn. And I suspect that in this case, no matter how many nodes I give it, it will probably not be able to learn this very well. We shall see. See, the loss is not very good. I probably can give it the modulo function inside the neural network somewhat. It should be able to learn this. But based on what I see so far, I doubt it will be able to learn it. Okay, let's see the output. It gave up. You see, it gave up. It just modeled one line like that. Yeah, too many notes here. So I think it was better when it was 100. Yeah, it was better when it was 100. I mean, okay, I don't have much time to continue this, but let me just put this as unsolved. Unsolved. Possibly need to encode the modulo operator as part of the model explicitly. Yeah, so there's some limitations in what a neural network can model because it can only model like addition pretty well. Like if you do multiplication, it may not scale that well as well. But here my focus is whether it can do an if else statement, and nah, I don't think this works. I need to tune it a little bit more. And yeah, I will try to stream this again. We see whether we can solve this modulo thing. It's quite interesting to me, and hope it's interesting to you. So this is something that I think modern neural networks don't do that well. Yeah, I mean, if the relation that we are trying to model is like quite obviously a piecewise linear, like for example this thing here, like here, it probably can fit that one quite well. It needs to be smooth also, smooth, piecewise linear. Okay, but if it's like this, where you jump like that, you probably have to map this thing, okay, into a way that the neural network can learn because it's not going to learn the modulo that well. Yeah. So yeah, next up we try to solve this. I'm trying to visualize how this neural networks work because like I think it's causing some problems for me in reinforcement learning. I tried to do like a neural network for Minesweeper if you've seen my earlier streams, but I faced the issue that it's not learning that well. So it might be the nature of the kind of networks that I use that could cause all these difficulties in learning. And yeah, we'll just discover them. All right, see you in the next stream then. And yeah, thanks for watching. Bye.